Thanks everybody for coming. This is the Refrigerant Regulations Design Implications session. So more about design. My name's John Rath. I'm Director of Operations for NY-GEO, which means I work for Jens and his fellow board members, as well as Christine, basically whatever they ask me to do. So I'm really honored to be here because this is a treat for me and I get to learn from you folks that are in the industry and have so much knowledge that I can use when I talk to other members. Just a couple things, repeat for many of you I know, but if you're here for credits or professional development hours, at the end of the session you need to come over here and I need to get a signature on either a filled already populated form or one that's blank, depending on whether you signed up at registration. Today, Jason Filler from FW Webb is going to talk to us about the refrigerant regulations. I didn't know it, but he's a real leader in right here in hometown, right? Hometown guy. So, and he's played really key roles in a lot of different big projects. HVAC with school districts, multifamily businesses, and so he's really got a pretty good depth and breadth of explanations. He, in fact, is sought out as an advisor on many, many projects. In particular, he shares his expertise with ASHRAE as a research promotion co-chair. But that wasn't enough for you, right? They either talked him into it or he volunteered to be on the technical committee 8.7, which is really, really focused on today's topic of variant refrigerant flow systems. So if you'll help me welcome Jason, we'll get started with this and have a great session.
Yeah. Thanks, John. All right. Well, welcome, everyone. Thank you for joining me today. As engineers and contractors, we know our industry's rapidly changing with our refrigerants. There's new regulations, new changes every day. So we're going to talk about today the new refrigerants, the new standards coming out, some of the recent news breaking the past couple of weeks on the EPA and refrigerant timelines. So we're going to get a little bit of everything. Throughout this presentation, if you got a question, just raise your hand and John will come over with the mic and we can answer your question then. You gotta see if this works. All right. So there's our agenda. So we're first talking about the refrigerant updates. Talk about A2L refrigerants, ASHRAE 34 and 15. Talk about how that applies to VRF designs and to the safe application of the new refrigerants, and we'll have some design examples. So, much like tariffs, the refrigerant transition timeline continues to be a moving target with very little clear guidance from anyone. So unless you're following the daily news cycle, staying up to date with the EPA or with everything going on with Trump, it's really hard to stay up to date to know what's going on. And every time I've done this presentation a couple times, and every time I do it, I have to update it a couple days in advance because there's something new breaking. And even today, I have some breaking news that was released about 2 weeks ago from the Trump administration. So we'll go over that too. So this is part of it. So we're gonna make refrigerant great again, right? That's the whole plan. And I put this meme in here on Trump as a joke, but it really did happen. He did sign another executive order that's called Protecting American Energy from State Overreach. So I want to thank Sarthak from CHA. He sent this to me last night, and I'm like, oh, I better add this to my presentation. So we're going to talk a little bit about the EPA and what they came through, and then at the end of this, we'll talk about what this new executive order is going to do. So I'm sure many of you saw this EPA headline that they're going to roll back refrigerant rules. They're going to start changing things. The EPA head, he called it the most consequential day of deregulation in American history. And the things they said they rolled back. It was more than refrigerants. There's a whole list of different things, but we're here to talk about refrigerant. So, naturally, anytime we hear this, that there's a change, everyone asks, do we need to panic? Are we going back to 410A? Are regulations changing overnight? Do we need to pump the brakes on all this A2L? So let me be clear here. The short answer, nothing has changed today with the EPA. This is mostly political theater. The EPA announced its intent to consider change. That's it. There's no new rules, no new regulations, no timelines have been adjusted yet. This is just them saying, we're going to look at this again. Anyone has any input, they're going to reconsider the AIM Act. So for right now, it's business as usual. And this was mainly driven by lawsuits and petitions filed by the food industry, who argued that a lot of the refrigerant transition deadlines were not able to meet on certain equipment like low temp refrigeration, reaching coolers, walk-in coolers, stuff like that. They have the furthest deadline down the road than anyone else. So, and this is kind of the rule change, but before we get into that, in general, we're not going to see a change in comfort cooling for A2Ls. The manufacturers have already made the investments in A2L equipment. Package equipment has already been released. Residential split systems have been released. We are far down the road to turn around right now. So really, unless you're in the business of refrigeration of low temp coolers and freezers, the rest of the HVAC transition is very much on track. So really, the EPA is really just more headlines than anything, just kind of political grandstanding. And if we get into the rule change, I'm gonna walk you through this so you can understand the timeline of how long it takes to change the rule. Because it's really important to understand this before we start hitting the panic button here. So again, first, nothing has been released from the EPA, no new proposed rule, no published regulations. It's just an announcement that it tends to make changes. But even once they figure out what they want to change and propose a rule, there's a very defined process that has to play out, and that's what you're looking at here. So step one, after they propose a rule, is there's a public comment period, which at minimum takes 30 days, where anyone can submit feedback. After that, the EPA has to review all those comments, consider them carefully, and then decide if they need to adjust any rules based on that. Then it goes through 2 rounds of review by the Office of Management and Budget, and that alone can take up to 90 days. So right there, we're looking at 6 months just to go through the review process. And then, once the final rule is published, the AIM Act requires a mandatory 1-year delay before any of those rules go into place. That's why we put this all together. We are realistically looking at 2.5 years before any regulatory changes could actually impact our industry. Now, could it happen faster? Yeah, that's what Trump's trying to do now. If the EPA really pushes it, we're talking about 6 to 9 months to complete that process. But even then, you're still looking at 18 to 20 month delay before anything goes into effect. So let's look at the current timeline right now. So this is the refrigeration. This is what we were talking about with the low temp coolers, reach and freezers. The reality is, by the time any potential rule change makes its way through the regulatory process, most of these key deadlines have already passed. In fact, some are already here. So you look at the self-contained retail food, manufacturing stopped in January. They do have a 3-year sell-through date. Full systems, this is probably where if there's any regulatory change, it's going to impact full systems for supermarkets. They have until 2027. Units or systems with remote condensing units, they have until the end of this year. So again, if you look at that timeline, there's no way there could be any changes made to that. And then same thing with industrial refrigeration. They have until the end of the end of this year to get systems installed. So there's no way, if there's any rule changes, that it would affect this equipment. Now, when we look at comfort cooling here, this is where things are moving even faster. And really, there's no way any rule change is going to impact this. So manufacturing cutoffs for rooftop units and chillers are already in effect for 2025. New York State chillers have been using A2Ls for a couple of years now. We've already stopped manufacturing residential and commercial air conditioners and heat pumps with 410A. But again, the install deadline at the end of this year is coming fast. So we're talking, 9 months away to the end of the year. And for VRF systems, the manufacturer cutoff is this year, and then we have a 3-year sell-through date for VRF systems, 410A. Now, if you thought the federal regulations was aggressive, well, lucky for us, we're in New York State. And we like to do everything just a little bit harder and try to be a little bit better than everyone else. So New York State has even more aggressive timeline. So first, the big thing here, the big headline here is VRF. You saw on the federal guidelines, they had a 1-year sell-through date. New York State, there is no sell-through date with VRF. The systems need to be installed and commissioned this year. No questions. And this is part of New York State DC Part 494. This went into effect in January. And this isn't a proposal. This isn't draft rule. This is law. This is it. So here's the VRF. I guess I got to hand myself here. Our VRF is right here. And then the big story here also, if you look in the red here, New York has a tighter deadline for ultra-low GWP. So what's that ultra-low GWP? We're talking R290, butane, refrigerants like that. And we're not ready for that. In 5 years, are we going to be ready for our R290, put propane in our buildings? I highly doubt it. We're getting there, but we got a ways to go. So here's a quick snapshot of the refrigerant market. Here you can see we got 410A on the left. We got what's made of, that's COP, and capacity change. So we look at 454B, slightly more efficient, little less capacity. So that's why if you guys have spec'd any new 454B rooftop units or residential splits, the equipment is much larger. The coils, the vapor coils, condenser coils need to be larger for greater heat transfer. R32 is a 100% pure refrigerant, and you can see this is much more efficient and has a higher capacity change, and that's why you're seeing R32 for a lot of VRF systems. In those systems, you're going to see that they have a little less charge in them than your 410A one. With 454B, we're already at 454 with package equipment and those split systems, but we have a shortage of 454B. I don't know if any contractors are in here and try to get some 454B. It's hard to get. Even as FW Webb distributor, we're only allocated a certain amount of 454B. There's only two manufacturers in the country that make this. And with all the equipment manufacturers using it and new systems using it, it's really hard to get. We're actually allocating each contractor only 10 cans of 454B when they buy it. On the other hand, R32 right here is a non-proprietary refrigerant. And there's plenty of R32 available in the market today. It is much cheaper. So for some perspective on pricing, R22, which I don't have on here, but it's right here. There we go. R22 for a 30-pound jug, $795 is the market rate. 410A, $175. 454B, $399, and R32, $255. So yes, R22 is still the king of expensive refrigerants, but R54B isn't exactly cheap either. So just want to kind of put that out there so everyone, understands kind of what the market limitations are right now. We're seeing contractors actually, and I don't recommend this, is buying residential split systems, taking the 454B gas out of it and recharging it 410A. Going to avoid your warranties. I can't say it's going to work, but That's how desperate some contractors are right now. So with the R290, kind of where we're going with the low GWP, New York, again, we're 5 years away from this. So we're going to see this in the industry moving forward. You know, if we have any people from Europe here, they've been using it for decades safely. A lot of their heat pumps are R290 right now. In the U.S. right now, it's most commonly found in freezers, display cases, small refrigerant systems, and you might even have it in your house right now in your refrigerator. A lot of those either use propane or butane in the refrigeration cycle. But in order to really get our arms around this, we need to start getting comfortable working around flammable refrigerants. And the A2L is a good start for that. What that means is no torches or open flames around the equipment, sparkless motors, so your fan motors, vacuum pumps, stuff like that, meeting ventilation requirements. That is a big thing with VRF. And with R290, with R290, right now with ASHRAE, there are strict charge limitations, so you can have no more than 150 grams of R290 per circuit. So that really limits you in what you can use right now and how you can design equipment. Another big thing, the R290 propane, it's not the same propane you have in your backyard with your barbecue grill. There is no odor in this R290, so you might think, oh, it's a leak, we'll smell it, no big deal. They can't add the odor to R290 because it messes up the chemical properties of the refrigerant. So it's completely odorless refrigerant. So that's a big thing we need to figure out. You think the A2L regulations are tight now, they're going to get tighter. So here's the big picture. We're currently living in an R54B world with supply chain limitations, and right down the road, it's going to be R290 in New York State. So now I have to admit, one of my favorite shows of all time is King of the Hill. For those of you not familiar with King of the Hill, he's about as Texas as it gets. He's a blue-collar, hardworking, loves his lawn, loves the Dallas Cowboys, and of course, he loves selling propane and propane accessories. So I posted this in 2023 on LinkedIn and showing Hank's evolution from selling propane. Now he's selling heat pumps. And I don't know if you can read it, but it says, I sell heat pumps and heat pump accessories. Now, if you told me 5 years ago it looked something different, I'd be shocked. So I think this is the new Hank Hill. I sell propane and propane heat pumps. So one of my all-time favorite shows. I love Hank Hill. All right, but I know I got a lot of doom and gloom with R290. There is some hope. Working its way through the New York State government right now is New York Senate Bill 235 and Assembly Bill 361. This is a bipartisan bill, and basically it requires New York State to align with EPA regulations and phase-out dates, and they have support for AHRI in this bill. So right now it's just making its way through committee, and hopefully it will go to vote soon. Now, the big news here is Trump signed an executive order protecting America from state overreach. So I'm just going to grab my phone here and pull it up real quick, because again, I just got this last night. So here's the headline here. In a move to ensure that energy flows as freely as our nation's spirit, President Trump signed an executive order on April 8th, 2025, aimed at keeping governments from putting too many roadblocks in front of American energy production. This order tells the Attorney General to hunt down any state law that might be overreaching, especially those targeting climate change policies, carbon emissions, or environmental justice that can make energy more expensive. So there is no rule change yet. There's no new regulations. Pretty much what that's saying is he's going to send the Department of Justice out to states that have crazy regulations and get them to align with the EPA. So this is going to take time to work through. They have to identify which states are overreaching or they feel like are overreaching. And then there's going to be lawsuits, whatever it takes to, whatever the Trump administration feels like they have to do to get everyone to fall in line. So keep your eye out for that. I'll definitely be monitoring it closely. If you Want updates, drop me your card. I'll be sure to email you if anything changes, but definitely big news. That was just 2 weeks ago. Now, as far as DEC 494 goes, there are some exceptions you should be made aware of. So the first one is if you have a building permit that was in place before January 9th to install a 410A VRF system, you have that 1 year sell-through date. Now, if your plans do not have permits or do not list 410A, you're out of luck. You got to switch it over to the A2Ls. But the DEC is talking to several stakeholders like the New York City Department of Buildings about expanding that exemption even further, which is going to fall in line with the EPA, where if you have construction plans that show VRF 410A, but you don't have building permits, they're going to try to extend that 1 year sell-through date to you. So that's not official yet. They're working through that right now, and so hopefully we hear more news on that in the next couple of weeks. So let's talk about those A2L refrigerants and propane, A3. So when we first started talking about A2L refrigerants, people heard the word flammable, got scared, kind of the first reaction, oh no, is the building going to blow up? Is there going to be a big fire? Kind of, thought about this, right? Kind of looks like the Hindenburg blowing up a little bit. But in reality, A2L refrigerants are only marginally more flammable than 410A. We're not talking about this. Here's your A2L, and here's your class 1. And what classifies it as an A2L to make it more flammable is you see outside this V here, that flame spread goes just outside that V. And they test the refrigerants inside a beaker, and if it goes just outside the parameters, now it's flammable. So that's really the big difference. It's not that big a deal, but with proper training, design, and safety protocols, we can all kind of work with it. So next, I got a quick video that really explains the flammability of the refrigerants. This is from one of the manufacturers. It's a pretty good video. So let's see if we can get this to play. No sound. 1 second. Here comes our AV guy. Should have warned you there'd be a video. Perfect. Thank you.
A key parameter in determining the actual risk of a gas to
Let me pause it.
is the mixture reaching its flammability limits in air. The lower flammability limit is important, as you need to have enough gas mixed with air in order for it to reach its flammable concentrations to ignite and burn. So if during a leak situation, the leak rate and the quantity released is large enough that it surpasses the lower flammability limit, flammable concentrations can form. Propane is a commonly used low GWP refrigerant in small refrigerated cabinets, but its lower flammability limit is only 2% propane by volume in air. This means that for even small charge sizes, the flammable layers can form and actually ignite and burn. You typically need 4 times more A2Ls to reach flammable concentrations as compared to A3s such as propane. Hence, A2Ls are inherently safer as you're less likely to form flammable concentrations. This means much higher quantities of low GWP A2L refrigerants are necessary just to be flammable, which means there are a number of leak scenarios for these A2Ls that would not even result in any consequential flammable volumes. Another key parameter in determining whether a mixture actually ignites or doesn't ignite is the minimum ignition energy, or the MIE. The minimum ignition energy is important, as most electrical components actually can produce electrical sparks under normal operation. unless they're specifically designed to actually avoid that. If the energy of the spark or the electrical discharge is higher than the minimum ignition energy, then in a specific leak scenario, we can actually ignite the mixture if flammable concentrations are reached. Propane has a minimum ignition energy of just 0.25 millijoules, which means that even a weak discharge, static discharge, say from your clothing, can actually exceed this value and potentially cause an ignition event. To give you an idea of what millijoules are, so say for example in the wintertime, I'm actually shuffling my feet on the carpet and I actually touch a door handle and I actually shock myself. That value is actually 20 millijoules, or almost 100 times higher than the energy necessary to ignite propane. In comparison, A2L refrigerant have minimum ignition values 2,000 times higher than that of propane, meaning much higher energy sources are required in order to obtain ignition. This also means that many commonly used electronic components can be used safely with Opteon XL refrigerant. The severity of an accidental ignition can be determined by many factors, such as reactivity, for example, how fast the flame burns, or burning velocity, as well as combustion energy. The higher the gas's reactivity and combustion energy, the larger the potential impact the accident can have on the surrounding area. To put that into perspective, the combustion energy of Opteon XL20 is approximately 5 times lower than that of propane. In addition, it's significantly less reactive than propane, where its burning velocity is actually 30 times slower. A key parameter in determining...
There we go. All right. Yeah, so it's a pretty good video. Explain the difference between the refrigerants and how flammable they are. So the key takeaways is the concentration of refrigerant required to air tonight. A3 is 2% of air. A2L is 4 times of propane. And A2L is 2,000 times higher than propane. 300 millijoules. Well, that's not right. That's an error on that slide. The A2L needs a 2,000 times higher MIE than propane. So in other words, while A2L refrigerants are classified as flammable, the conditions need to be just right for them to ignite. So you don't have to worry about static electricity or anything like that with A2Ls igniting. So, all right, so we're going to get into a couple ASHRAE 15 and ASHRAE 34. So where the A2L and A3 comes from, it comes from ASHRAE 34. ASHRAE 34 defines the refrigerant concentration limits through toxicity, flammability, and oxygen deprivation. And you can see on the bottom here kind of the difference. So A1, no flame, A2L, lower flame, and then A3 is at the top. So this all comes from ASHRAE 34. Now when you're designing with ASHRAE 34, you can't do it without ASHRAE 15. ASHRAE 15 is going to be your design guide, and then ASHRAE 34 is going to give you the formulas you need, the LFL, the lower flammability limit, and all your key information on refrigerant that you're going to use for ASHRAE 15 to plug into your formulas. So ASHRAE 34, what we use for 410A is the refrigerant concentration limit when we're designing around ASHRAE 15. So right now, 410A per 1,000 cubic feet in a commercial space is 26 pounds. In an institutional space, which has stricter requirements, it's only 13 pounds. So it's important to know the refrigerant concentration limit. This is the safety limit that counts for both toxicity and flammability. It's a broad safety measure that covers everything from respiratory health and flammability risk. Now, when we look at A2L, they're not using RCL. They're using the LFL, the lower flammability limit. And you can see your releasable charge is about 1/5 of 410A. So we're talking 19 pounds of R32 in a 1,000 cubic foot area, or 5 pounds in institutional. You go back, there we go, 26 pounds. So that is a huge difference right there. And that's why we're here to talk about kind of design considerations and how we're going to work around those limitations. It's important to know that the LFL is just looking at flammability. It's not looking at your respiratory health, anything like that. It's just looking at how much refrigerant is in the air or in a space that can safely disperse without being ignited. And ASHRAE 34, for all your different refrigerants, it's going to give you this LFL value, whether it's 454B, R32, whatever it is. Pull out ASHRAE 34 and you'll get that information there. So we're going to use this in ASHRAE 15. And the first step to applying to ASHRAE 15 is identifying your safety group classification of the refrigerant. And this comes down to what type of system you're designing around. So let me back up there. So the occupation classification, that's what we're talking about: commercial, institutional, industrial, public assembly. That's going to adjust your occupancy factor and your EVDC. And we'll talk about that more in a minute. Your system probability, that is your equipment. So most equipment, you can see is high probability. That's your rooftop units, splits, heat pump, VRF, and PTACT. And basically what a high probability system is if there's a leak in the system, it has a more likely chance of entering the occupied space. So if a rooftop coil leaks, that's going to go straight into the building. Or if a VRF system leaks, that pipe's going to leak into occupied space. A low probability system is really, the way I look at it, is anything without a fan, like a water source, a water heat pump, a chiller. If there's a leak, it's most likely going to stay in a mechanical room or a machine room where it's not going to get into that occupied space. So those are different factors that we look at when we're designing around ASHRAE 15. For today, we're going to focus on high probability, because that's what we're mostly working with water heat pumps, with VRF systems, split units, and that's where most people are going to be around. So A2L. So when you first start around the A2L, before you do anything, before you pass go, before you collect $200, you need to make sure your equipment is UL listed, UL 60335-2-40. And this pretty much means it meets all the new A2L regulations with the sensors, sparkless motors, stuff like that. So that is step one before you do anything, get your design. Make sure you're using the right equipment. That's really important. So UL and standard 15, they're a little bit different. A lot of the manufacturers are going to use UL listing for their equipment, but when we design, we're going to be using ASHRAE 15. So the difference is the UL prescribes several methods for the manufacturer to measure and calculate the releasable charge. This may result in a higher or lower releasable charge than in ASHRAE 15. ASHRAE 15, as we talked about before, you have these different classifications that you're going to use to factor in your releasable charge. In an institutional place, you have a lot lower releasable charge than a commercial space. ASHRAE 15 also has different standards for the RDS, for the refrigerant detection systems, where UL does not explicitly require one. So that's a big difference right there. You need to know your charge and if you need a RDS system or not. And then lastly, the way that the manufacturers calculate their releasable charge is they use a set square footage, set ceiling height to calculate their releasable charge, where ASHRAE 15 is based on the room and your occupancy classification. So here's what the A2L equipment looks like. Has anybody used A2L equipment yet? Show of hands. Okay. So we're looking at, here's a return air of a rooftop unit. A rooftop unit, you're going to have an RDS in your return air. Depending on the size of it, you might have two. Here's a coil from a split system. It's going to be mounted on the outside with your sensor on the inside. And again, the RDS, it must come built into the unit. It must be integral and listed with the unit. You can't use a third-party RDS. You can't use whatever you want. You have to use what comes with equipment. A big thing is RDS is not required for any charge below 4 pounds. And this is your releasable charge, a lot different from your full charge. So you have different circuits. You gotta look at a single circuit. Your first point of failure is what they're gonna look at here. So the RDS requirements. So if the RDS system goes off, alarm's gonna go off within 30 seconds of exposure. These sensors are also pre-calibrated. They cannot be adjusted in the field. You cannot modify them. They come as they are. Shall resist poisoning pretty much means they're not gonna degrade over time. If there is a refrigerant leak, they're not gonna get damaged. They're still gonna work. Long-term stability just means under the right conditions, it's still going to work. So temperature, relative humidity, pressure, all that, the RDS is still going to work. And it does hourly self-testing. And if it does fail, alarm will go off. And then self-termination of end of life. So think about your smoke detector in your house. When that battery goes out, you just hear the beeping, and it's usually like 2 o'clock in the morning. The RDS is going to be the same thing. And lastly, it should be accessible and serviceable item. So it can't be buried somewhere. These RDS systems have a life expectancy of 10 years. So if you're a contractor doing preventive maintenance, it should be part of your preventive maintenance log, checking the RDS system, and knowing in 10 years, you're probably gonna have to replace the RDS before you replace the equipment. So what are the mitigation actions when the RDS goes off? So first thing it does is shuts off the compressor and turns on the fan to circulate the air. If you have a mitigation system, it's going to initiate that exhaust system. It's going to open all zone dampers. So if you have VAV system, anything like that, it's going to open all the zone dampers, any electric heat, any electric source in the ductwork, it's going to de-energize that, and obviously close off your safety valves. So it's going to do this for 5 minutes. Test again, reset, and the alarm will go off again. And most likely, if it goes off a second time or third time, the unit's probably out of refrigerant and stripping on low pressure. All right, so here's the real fun part. What we're going to use instead of our RCL calculations in ASHRAE 15, now we use the effective dispersal volume charge. And this is the maximum refrigerant charge permitted for an effective dispersal volume. So your refrigerant charge of a direct system or your releasable charge cannot exceed your EDVC. A big difference between this and the A1 is the A2L. You include your occupied and non-occupied spaces in your EDVC. So your EDVC, so first thing you gotta do is figure out your effective dispersal volume. So that's the area where the unit is serving. So it's either this conference room, it's a bedroom. You gotta figure out your volume, your lower flammability limit. As I mentioned, you get that from ASHRAE 34. Then you're going to multiply that by a concentration of 0.5. That is a set value. And then depending on your occupancy, it's either going to be commercial, institutional. If it is institutional, we cut it in half. So it's multiplied by a factor of 0.5. So that's kind of like the real high level overview of your EDVC, but that is the biggest change going from A1 to A2L when you're designed with refrigerants. There is one big exemption in here, which I really appreciate. So any continuous run or refrigerant piping or joints that have been tested in accordance with 9.3, essentially it's been tested under pressure, there's no leaks, those are exempt from your spaces. So if we had refrigerant pipe coming down the middle of this conference room, we would not need to calculate this conference room in our EVDC. It is exempt space. Or a lot of times you might find continuous runs of refrigerant pipe in a mechanical room. You don't need to worry about refrigerant leak into that mechanical room. And the big thing I would suggest to contractors is instead of using hard pipe, maybe consider line sets, using soft copper. They come in reels of up to, I think, 167 feet. So that'd be a way to kind of avoid additional refrigerant detection mitigation actions. The big thing using soft copper, actually, you don't want to see spaghetti noodles up the ceiling, so make sure you use enough clamps and hooks to make sure it is properly installed. All right, so say you get to your EVDC and your space is too small. How can you make it bigger? So ASHRAE 15 has something called connected spaces, and there's a couple ways you can connect spaces. Number one is through permanent natural ventilation opens, through ductwork, or through mechanical ventilation. So you can take 1,000 cubic foot area and turn it into 2,000 feet. So These are different options you can use to connect your space. And you're going to have to use this a lot more with these VRF systems or any split system where the space is too small. If you can figure out how to expand your volume, then you'll be in good shape. So natural ventilation. I know there's a lot of words on this, but there's a lot to go over here. So first is previous versions of ASHRAE 15 kind of left up to the design engineer to decide on what is natural ventilation, how big to make the louvers. So now the new version of ASHRAE 15 set specific requirements for those natural ventilation openings. They provide equations. So if you're going to put a louver in, they provide equations to size those louvers. And I think the big thing is the bottom of the opening has to be no higher than 12 inches above the floor. So previously, if you're doing a rooftop system, you might put a transfer grill above a door. That's not going to fly anymore. You would have to put it pretty much at the bottom of the wall. And that's because refrigerant is heavier than air, so it's going to collect at the bottom of the floor. So you want to put those natural ventilation louvers or grills where the refrigerant's going to collect. Ductwork, you can use ductwork to connect spaces, and when you do your EVDC, you're going to include the volume of the ductwork. So your supply, your return, ductwork, you include that all in your calculations. If you have dampers, the big thing with dampers is it can't close below 10% of the design airflow. And then you can also include ceiling or floor plenums in your space, which is great. So you do have some options to expand your room volume. Mechanical ventilation gets a little more tricky. The big thing with mechanical ventilation, this is different from 62.1. So this is not about air quality. So your DOAS unit does not count for mechanical ventilation. This is strictly a safety mitigation. So mechanical ventilation is used to dilute and remove leaked refrigerant from a space during a leak event, not to condition the air. And you're most likely going to use this for a machine room or any equipment where you might not have a fan to circulate if the RDS goes off. So the fans used for this, you need to have separate exhaust and supply fans. You need to do two complete separate systems. Fans need to be UL 505 or UL 705 listed. They can either operate continuously or activated by the alarm. The makeup air must be positioned to allow makeup air to mix with the refrigerant, so it's got to be lower to the ground. It can't be like a high exhaust. Again, same with the intakes and the exhaust, 12 inches, no higher than 12 inches above the floor. And this is pretty common, or, discharge prevent air recirculation of exhaust air. I know we've all been to sites where the exhaust and the supply air are right next to each other. So we're not talking, fumes anymore or grease. This is refrigerant. So we need to make sure that those are designed and installed correctly. And again, flammable refrigerants, no ignition sources, no open flames, and monthly testing. So this mitigation system needs to be tested monthly. So another thing to add to any preventive maintenance schedule that you're doing. And lastly, for 2024, ASHRAE 15 released the new standard. 2 or more spaces connected by mechanical ventilation system complying with the requirements. The volume of all such connected spaces should be included in your effective dispersal volume charge. So again, that's just saying if your space is connected by ductwork, you need to account for all those spaces that are connected. All right, so this is new for VRF systems. This is your refrigerant changeover box. So this is a high concentration of refrigerant in this box. You can no longer just throw this up into a corridor or a machine room. It's going to have a duct collar on it now to exhaust that refrigerant out. And this needs to stay in a negative pressure because, this can contain, several pounds of refrigerant. You don't want that leaking out. And ASHRAE 15 sets a minimum exhaust flow rate of 11 CFM. So you got to be conscious of where you are installing these in your building. You need to make sure there's an outlet. You don't have to exhaust it outside. You can exhaust into a larger space where there's enough volume to compensate for whatever refrigerant is in this box. And as the new equipment comes out with the new refrigerants, the VRF manufacturers are going to provide your selections that show how much refrigerant is in this box so you know what to count for in your calculations. So everyone's favorite topic, shaft ventilation. This has been the heartache of every multifamily contractor out there, is trying to figure out how to install split systems with this new shaft ventilation system. So the shaft containment requirements, so anytime refrigerant passes through 2 or more floors, the roof doesn't count. So if you go from the roof to this top floor, you don't need a shaft. As soon as you go down to the very next floor, then this all needs to be in a shaft. So that's pretty important there. So we got a couple options for shaft ventilation. We got mechanical and natural ventilation. Here we're showing the natural ventilation shaft. So the shaft pipe should be duct or conduit, minimum 4 inches. At the lowest point here, it needs to be pitched downwards outside. So again, refrigerant heavier than the air is going to sink to the bottom of the shaft and go out. And there should be a makeup air opening at the top to promote good draft going down the shaft there. So that's pretty simple. And you can run other utilities through your shaft. So if you got any electrical waste, whatever, you can run it all through the same shaft. It does not have to be just your refrigerant lines. So here's another picture here to showing shaft here. And then outside, my recommendation, if you can run your refrigerant lines outside, that's much easier than trying to ventilate something inside. So your mechanical ventilation requires a little more work to design. So you got minimum air velocities you got to keep depending on the shaft volume. You're going to have an exhaust shaft and a makeup air shaft. The big thing with this is you're going to have an RDS at the bottom of the shaft. So if there is a refrigerant leak, it's going to pick it up. And your exhaust fan, this can operate continuously or based on when that RDS goes off. And it's going to go off if it's 25% of LFL. So here's a kind of a picture of what the top of the shaft would look like. So one side, you're going to have all your refrigerant piping and then your makeup air. So we talk about exemption on the top floor. Again, you can route domestic water, electrical, communication, your sprinkler lines all through that same shaft. So you can design that shaft big enough just to run all your utilities through it, or design it small and just run your refrigerant lines through it. It's really up to you. So townhomes, do a lot of townhomes. When you're townhomes, or anytime you're really mounting a condenser on the ground here, run your refrigerants on the outside. That's the easiest way to ventilate them. But then when you go from, you're in the attic, you go from N to where either your fan coil or your air handler is in the attic, or say you got, a high-rise system right there. There's no requirements. This does not need to be ventilated. It is an unoccupied space. Again, if you remember, let me back that up. It doesn't mean related if you meet the exemption of where the pipe is pressure tested in accordance with ASHRAE 15. If it is not pressure tested, does not meet that standard, then it needs to be in shaft. I mentioned using line sets and soft copper. This is a perfect application. So you can make your joint connection out here and then run soft copper in there with no joints or anything, just going to the unit. And that's all good according to ASHRAE 15. I should note that ASHRAE 15 is way ahead of any local code. I think local code in New York State, they're still operating off ASHRAE 2018. Someone correct me if I'm wrong on that. So always consider your local code when you're designing these line sets. So prohibited locations for refrigerant piping. You can't install in a fire-resistant corridor, interior exit stairway, interior exit ramp, passageway, elevator, dumbwaiter, so any place where it's going to be really an egress where it's emergency escape. The new in ASHRAE 15, they define the passageway definition. It used to be like in a school, like hallway is considered a corridor, so they have clear rule around that where exit components separate from other interior spaces of a building or structure by fire-resistant rated construction. So keep that in mind there. So we'll get into machinery rooms. Machinery rooms is a big deal with the A2Ls, whether it's a heat pump or a chiller. This is just the ventilation requirements. There's a whole other set of building requirements when you're doing a machine room. And when I say machine room, don't confuse it with like a mechanical closet where someone has an air handler, or we talk about refrigerant pipe and run through. This is like a separate room from the building, no penetrations into the main corridor, all the duct penetrations are sealed. So keep that in mind. This is a machine room. Think of a chiller or a boiler inside of it, not a typical mechanical closet. So again, it has very strict ventilation rates. Just like in a occupied space, it can run continuously or activated by alarm, vented to the outdoors. The fans must be separate and have separate power, electric non-spark motors. And the makeup air, you can't steal makeup air from another area. It's got to have its own makeup air. And the inlet locations, again, the inlets and exhausts have to be low. So here's more of the requirements. You got your set point requirements here. The big thing is automatic self-testing and annual and monthly inspections of your refrigerant detectors. Another thing is alarms. So not only do you need a visual alarm inside, you need one outside as well, and manual reset inside. So those are two big things different from previous versions of the machinery room. So talk about the ventilation. ASHRAE 15 has under Section 8, they have ventilation requirements. So I just did an example of a small heat pump here. It's got 27.5 pounds. That would be, 40, 50 ton heat pump. We got a small machine room here, 6 by 10. And then our refrigerant pressure is 425. So I'm not going to go through the formula. I don't want to bore everyone to death by going through formulas. But we're going to take our machine room, our minimum airflow per table 8.2, and we're going to plug in our formula here. So we got our refrigerants here, we got our refrigerant pressure in P, and we're going to plug all that in. And for that one little heat pump, we need over 3,800 CFM of ventilation. This seems to be the biggest issue, I shouldn't say issue, challenge is a better word for it, with machine rooms with the A2Ls. And this is a tiny room. It's 6 by 10. We usually have more room, but in this small space, we need a lot of ventilation. So imagine having to add exhaust and makeup air to this kind of space. What time do I have to?
You need to start.
Okay. All right, I'm almost done here. All right, so we'll get into the design considerations real quick. So here's a typical VRS system in our office. We got indoor heads in each office here. Each office is 10 by 10, 10-foot ceilings. So again, the releasable charge cannot be greater than your effective dispersal volume charge, your EDVC, right? This is how we typically design something. And these could be water source heat pumps too. So if we're using R32, our total refrigerant charge is 27 pounds. Our releasable charge on a single circuit is 27 pounds. So our EVDC is 9.55 pounds. That's how much refrigerant we're allowed to release. This unit has 27 pounds. So it does not meet the requirements. So how do we get around that? We talked about using ductwork and your plenums. So now you can take a fan coil, VR fan coil. They make zoning kits now for this, where each room can have its own thermostat, its own zone damper. And now you increased your effective dispersal volume. So instead of one room, now you got 3 rooms plus the fan coil. And if this isn't a plenum, you can include all that plenum space in your calculations. And we're also going to have a lower refrigerant charge because we have less indoor units. So quick calculation here. Now by combining this, our EVDC is 28.65, just over our releasable charge. So we are in compliance with ASHRAE 15. So again, we're connecting spaces to increase our volume. Mechanical ventilation, this is kind of like a funky example because I don't think anybody would put mechanical ventilation in an office, but this is just to show you kind of what would be required, and too far. So in this little space here, you need 456 CFM of ventilation there. Some more design considerations. Talk about these fan coils. You put your door undercut there. This is an older slide. This is from 410A. So this right here is no longer valid because it's too high. It needs to be no higher than 12 inches off the ground. Ducted fan coils, we just talked about that. So each room having its own fan coil, you do a ducted one and duct 2 rooms together. It's a great way to take care of that. And here's another example of using that plenum, because now you can use this entire plenum space in your volume calculations. That helps you meet ASHRAE 15. Another thing that's going to be coming down the road as you guys get selections from your equipment reps on ASHRAE, on VRFs, is the safety shutoff valves. These are actually field installed. They come from the manufacturer, but they're field installed. So typically they're installed right at the refrigerant changeover box. So if you find that if they're installed all the way back in your box there, that you don't meet the releasable charge, just move it closer until you meet it. And the manufacturers can provide you with how much refrigerant is between the indoor unit and that valve. It's not an easy calculation because it has to do with a lot of refrigerant pressures, how much volume is in the pipe, how much volume is in your evaporator coil there. So the manufacturer should be providing you that information on how much charge is between that valve and your indoor unit. Here's an example of a water source VRF system. This one's kind of funky, the way we have to do it. This is basement, first floor, and I split it up, second and top floor. So this is a typical design here. This is a 92-pound system, 32-ton unit. We got 18 indoor units. So we first designed like this, and we didn't meet our EVDC because of all these units, all this refrigerant charge is going out here. So we all right, this is it. So we instead of doing 2 condensers, we added much smaller circuits to stay within our EVDC. So connect spaces, lower circuits, lower refrigerant charges, smaller units will all help you get into compliance. All right. Can I ask questions? All right. So what is the key difference between A2L and A3 refrigerants? Boom. There you go. A. According to ASHRAE 15, when is refrigerant detection system required? When the system has a releasable charge over 4 pounds in a ducted system. What standard must A2L HVAC equipment comply with to ensure safety? This is the equipment, UL 60335-2-40. And then I think it was the last question. Which method can increase? I'm going to let you guys answer this one. What method can increase the effective dispersal volume charge in a space? There we go. Good job. You get your PDH credits. Thank you.
Great job, Jason. That's a lot of slides. Really appreciate the work you put into it. Yeah. The slides that Jason has provided for everybody will be on our NY-GEO website. Give us a week or two to get them on there, and also the recording of Jason. So great opportunity. Use it as a resource to get questions answered. Unfortunately, I want to respect your time. We've got 15 minutes to the next session, so we're going to have to pass on questions.
I can stick around.
Yeah.
If so, questions.
Again, credit people, come on up and we'll take care of that for you. Thank you very much, Jason.
Yeah, thank you.
Okay.